being made in the measurement, so we get this. And then we take the newer one, we do this, and then we essentially say, would this mean value of the new one, what's the probability it was drawn from the old distribution? Okay, if it was significant, if it was over here, you say, oh, there's a pretty good chance that the new one is not really significantly faster, because you could have done no improvement whatsoever, and there's a pretty good chance that it would have been drawn from this population, the old population instead. However, if it's drawn over here, which is, let's say, 4 sigma or 5 sigma away from the old mean, then you say it's a very, very low probability that this sample of the new came from that distribution, so we'll say that it's a different distribution. So the hypothesis that nothing changed is false. Okay, it doesn't mean it's necessarily faster, and now you're going to hypothesis testing, and so the whole religion of hypothesis testing, that if it's to the right and it's beyond 3 sigma, you can say, like, with 99% confidence, I'm pretty sure it's improved. Okay, but if it's not, then it's a statistical error. So any graph, and I'll stop with this because this is something I always hate, any graph in any paper that looks like this is okay, so here we have some variable x, and here we have fx, sorry, some y, let's say, and this is the old, and then we have new. Okay, and this is a typical graph found in a typical paper in systems, my area, which is terrible with its statistics. It's really bad. Any graph like this, there's only one thing to do with it, and that is to take a big line like this and say, no, paper is rejected, because these guys have no clue what they're doing. Okay, and the reason is because it could be the case that the old was actually, had the error bars, as we call it, could look like this. Okay, if this are the error bars on the old, the orange bars, it could just be that you happen to test the new on you just got lucky. Okay, you got lucky and you just happen to be within the error bars of the old, in which case new is not statistically significantly better than old. You just got lucky. Okay. And so without the error bars, you have no hope of knowing what's going on. Yeah?
Would it be possible for you to sample the new like several times and then find the error?
Yes, you can. As you take more and more samples, the error bars are going to shrink. Okay, and so then you get these small error bars, and and so when you have smaller error bars, then you say, yeah, statistically new is a lot better than old. But if you don't have any error bars, you just have 2 lines. Okay, we know nothing. We know nothing about it other than you got 2 lines. Congratulations, you know how to do experiments twice. That's all you know. And so I wish I could reject every paper like this, because it would save me a lot of time. But my program committee colleagues insist that these papers are actually good papers. So papers that have won best paper awards at conferences like SIGCOMM, which is considered to be a good conference, have these kinds of pathetic graphs in them. And it's just bad. Please don't make this mistake and use this as a way to reject papers. It's a good thing you can do for the service of science and humanity. And also you'll save a lot of time, because you can just quickly reject papers. Statistical methods are inadequate. Please repeat experimental section, and I'm done with that one. Okay. That was the central limit theorem. I'm going to quickly state the strong law of large numbers, and we'll revisit it later. And then we'll take a break. We'll revisit it when you do information theory. So, strong law of large numbers. Here we go. So this is an easy result to state. And the strong law says that the probability limit n tends to infinity. Again, we're talking about sums of equal to mu. Okay. And this is for xi are independent. And then identically distributed. distributed random variables. So the IID, as we call them. Oops. IID, as we called them earlier. Okay, and they all have the same, obviously the same expected value mu. It doesn't matter what the distribution is. Again, we don't really know what the distribution is. We don't care. But as we essentially add up more and more of these, as we compute the mean over larger and larger samples, okay, that's the way to think about it, then we are definitely going to find the true population mean in the limit. Okay. Now, this is kind of obvious when we have a finite population. Okay, if you want to know the mean height of all the zebras in the world, when n becomes the number of zebras in the world, then obviously it's true, right? When you have infinite populations, okay, and of course in the universe there are no infinite populations, but even if the infinite populations, what this tells us is that we're going to find the mean eventually no matter what. And so this strong law of large numbers, when used with the central limit theorem, is basically what's giving us the ability to test hypotheses and do all the stuff that we do in statistics. So this is a kind of an important result. In the book, I actually had a little figure. So what I did was I wrote a small program which just basically generates random numbers, uniform random numbers in the range 0, 1. And then it just adds them up and computes the mean. And so I just basically compute, you know, the means of the first k, and then k plus 1, k plus 2, etc. And as you see over here, you know, as you increase k, it goes up to the mean, which is the mean of the uniform distribution, 0.5. The funny thing is, till about 50 or so, it's actually pretty, it varies quite a lot. It's not very close to 0.5, even when it gets to about 50 or 60. And, but of course, 60 compared to n infinite is very small. Okay, as n goes to the limit, you certainly have this going on over here. So, yeah.
I wonder why it has to wrap this equation with the probability of 1.
Okay, so this is a form of a strong law of large numbers, right? Where we are, because it's a mathematical theorem, there's some kind of depth to it, right? I could just say limit n tends to is equal to mu, okay, and then ignore the probability, right? The probability around it, okay, essentially is taking care of all sorts of weird cases where for some reason this is not actually going there, okay. So I guess the easy way to put it is that you could state it without the probability, limit n tends to infinity is equal to mu, but that would not be mathematically correct, because I guess there's some crazy case where it's true. Yes, Nancy.
Can I answer this?
Yeah, please answer it, because you know more about this than I do.
I think it's the strong law of large number and because it's big law of large numbers. In big law of large numbers, the probability of this being mu is like, you say that this sum goes to mean in probability.
Right.
Converted in probability. But here you're saying that it's converted almost surely.
I'm not sure, yeah.
So you're actually saying that the probability of infinity often happening of that event is actually a series of events. That for example, you can define the series of S of n over n being mu. We can this series the probability of this infinity often happening is 1.
Yeah. So let me explain it in a slightly different way, okay? Remember when I talk about zero probability events, okay? The kind of weird things. Let me bring you back to zero probability events, okay? Let us say that I am going to do something, okay, where 5 times it's going to do the wrong thing, okay? So I'm going to toss a coin, and 5 times, and only 5 times it lands on its edge, okay? And every other time it's not going to land on the edge, okay? It's going to land of heads or tails, but only 5 times it's going to land on the edge, okay? Now, I ask you, what is the probability that it lands on the edge, okay? Well, it happened 5 times, so it's not 0, but you can make it as close to 0 as you want by doing as many events as you want, right? I can have 1 million and 2 million and 1 billion and 1 trillion events, but out of this trillion events, only 5 times it came up. So is it probability 0 or not? In number theory, if you can make a number or a ratio as small as we want, we'll call it 0. But it's not really 0. Okay, so in the same way, we have this term called almost surely, AS is abbreviated, almost surely means that in an infinite set of events, it can happen no more than a finite number of times. So that the probability of that in the frequentist approach can be made as small as we want. So it's sort of 0, but not exactly 0. Okay? And that's what's going on over here. So here we say in probability it's 1. And in probability it's 1 means that there can be these weird pathological cases where it does not become the mean, but it's only a finite number of them. Okay, and I think that's what Nasser was saying in a bit more abstract way, but what he's saying and what I'm saying are the same thing. Okay, and the way to understand this, another way of understanding this is, imagine we have the following situation. Okay, I have this kind of imagine that I have a roundabout. Now you've seen these roundabouts on needles, right? You know the roundabout, right? The traffic circle you go. So you're allowed to go through 2 traffic circles, but once you come to the 3rd traffic circle, you always go round and round. You never get out. You never get out forever. Okay, even when your gas runs out, you keep walking and walking until you die. Okay. Now, I ask you, what fraction of your life did you spend on the roundabout? Okay. Well, almost surely 100%, because the amount of time you spent in a knot in the roundabout is finite, and the rest of it is infinite. And so the ratio can be made as small as we want. So this is what I mean by saying you want to cover yourself just in case there's some weird cases where the limits don't exist. And mathematicians are very good at finding these bizarre cases and saying, oh no, at that limit it wouldn't go to mu. Well, that's okay. It only happens in a finite number of cases and have an infinite number of other things to worry about, so it's okay. Right? And when we do Markov chains, we study Markov chains, you'll find that the so-called non-repeating states, okay, transient states, are going to be have this weird thing, probability 0. It's finite in an infinite set. But in all practical cases, it doesn't matter. In all practical cases, you can kind of ignore that probability. Let me first start with joint events as opposed to joint random variables. Okay, so let's be careful. So we have joint events and we have joint RBs. These are different. Okay, so let's consider a simple event such as I roll a die and the face comes up as I have 6 outcomes. And for the sake of simplicity, I'll call each outcome an event. So I have 6 events. Okay. And then I'm going to have the, let's say I toss it again. I roll the die again. So I get the 6 more events. Okay. So now we already remember, hopefully, about joint processes. So corresponding to joint processes, we have joint events, which look something like this: 1, 1, 1, 2, all the way up to 6, 6. And this is a joint event. Okay. And if you continue the process more times, we can add more to the tuple, and we get basically joint events, right? So this is just reminding you of that. Now, what about random variables? So let's say I have a discrete random variable x, which has its domain 0, 1. And we have another random variable y, which has its domain 0, 1 as well. Okay. Now, if x has a domain 0, 1, okay, I should probably say x domain equals 0, 1, just to be clear. Now, because this, I can define the probability that x assumes every value in the domain. Okay, so we have probability p that x equals 0 and the p x equals 1, and we have probability p y equals 0 and probability y equals 1. So these are obviously probabilities that I can define for each random variable x and y. These are not events now, these are random variables. Okay. Now, in the same way that I have joint events, I can define the joint random variable, which is denoted either xy or sometimes x comma y, okay, we can write the joint as being essentially the probability that the joint variable, okay, the joint variable is x and y together, takes on the values in the product of these domains. Okay, so obviously the variable is going to take, the domain is going to be the cross product. It's going to be 0, 0, 0, 1, 1, 0, 1, 1. Okay, and we write this as pxy just to remind us. So here we can say px just to remind us that it's a probability for the x, it's a probability for y, and or we can write p x comma y. So in information theory typically we use x comma y, and in probability theory we use xy. And so we have this joint distribution over the cross product of the domains, okay, and we view this over here, this combined thing over here, as a joint random variable. Okay, that's the that's given the name or denoted xy or x comma y. Okay, and this is the domain. So this joint variable is basically just like a regular discrete random variable. Okay, it has some domain, and associated with each element in the domain, it has a probability, right? And it could be arbitrary. Okay, there's no particular reason why we can't assign any values if we want to the elements of this domain. Just like you can assign arbitrary values to the probabilities in this, you know, there's no particular reason. Okay, we can assign it over here. But there is a special case. In the special case, we can determine the probability of a joint value, this one, as the product px 0 times py 0, which we interpret, we write it more carefully as probability x equals 0 times probability of y. Okay, okay, we can, if this is true, xy equals 0, if this is true, then we claim that x and y are independent. In other words, the joint distribution is the product of the individual distributions, which we call the marginal distributions. Okay, these are called the marginal. If the underlying elements are independent. If they're not independent, then we don't know what it is. Okay. All right. So any questions about this so far? Okay. Yes. Beg your pardon? I'm considering this just for now, just the special case 0, 1, but in a moment I'll generalize it. Yeah, in a moment I'll generalize it. I just want to make the concepts clear for this. You done?
So yeah, always put the subscript of x and y, and then you also say x equals 0, y equals 0. What's the difference in both?
Over here you mean?
Yeah, there.
Here. So I'm doing it just for clarification, okay? But once you get into it, people will not show pxy. They'll just assume you know that the underlying distribution is a joint distribution. Okay, this is just for clarity. Okay, this is just sort of beginners. But once you go into it, we'll just say p x comma y, and it's assumed that talk about p the joint distribution xy. Okay, in information theory, we don't have we don't write p x y. We just write p x comma y, and it's assumed. Okay. But this is for clarification. In fact, nobody writes this either. They don't write px x equals 0, py y equals 0. They just say px 0, py 0, where px 0 is assumed to mean the full thing, probability in the distribution of random variable x that the random variable assumes the value 0. Okay, and so it's just abbreviated like this. And even further abbreviated typically is just p0, or something like that. Okay. All right. Any questions, Sal? Any other questions? Okay. So let's think for a moment about what we need to describe a joint distribution. If we take the individual underlying distributions x and y of these random variables, Okay, so let's extend it. Instead of 0, 1, let's say I have, d sub x of this, and I had d sub y. So dx of this and d sub y of that. Okay, then the product x, y in the joint distribution is going to be a cross product. So we're going to have dx times dy terms over here, which are arbitrary, right? So let's say dx is 1,000 and dy is 1,000. You're going to have a million terms, okay, because the joint distribution can take a million different values, okay, corresponding cross product. In order to specify it, I have to specify a million values. I have to say, okay, for each of these 1,000 values of x is, and 1,000 values of y, the cross product, I'm going to specify. It's very large. However, if they're independent, then we only have to specify 2,000 values. Here are the 1,000 values for x, 1,000 values for y. Now we know. It's very simple, right? It's exactly like having a matrix where you have essentially the domain x, you have dx like this and dy like that. And instead of specifying all the matrix elements, I just specify the the header and the columns, the two header columns. And then if I take the product, I find these over here. So if x and y are independent, life is great. Okay? And we can make the joint distribution, we can compute the joint distribution quite easily. If it's not, it's just an arbitrary distribution. That's what you need to realize, an arbitrary distribution. Okay? And yes?
We have a joint distribution of field guards x, y, and z. Do we call probability of x, y joint distribution or not? So if we have a joint distribution of field guards.
Okay, let me come to that in just a moment, okay? So I want to first do this, get this concept straight, okay? And then we'll do that, okay? So, but is this part clear? Okay. All right, so let's do the homework problem, because hopefully that will clarify things. So the homework, instead of using 0, 1, just for clarity, I used, where did I put it now? I used the different domains. So in the homework, I had the following thing. I had the domains for x, the domain was 0, 1, and for y, the domain was AB. And I specified actually the joint distribution as P0A equals, and you notice I'm not putting over here Pxy, I'm just saying P0A, but it's assumed that it's Pxy. Okay? So P0A is 0.1, P0B equals 0.5, P1A is 0.2, and P1B equals 0.2 as well. So the first thing was, what's the marginal distribution of x? Okay, so we're given this. Okay, I want to know what is the marginal distribution of x. So what is Px, x equals 0, and what's Px, x equals 1. And that is the marginal distribution of x. Okay, so the way we do it is like saying, okay, 0a is 0.1 and 0b is 0.5. So the probability x is 0 has got to be the sum of these two, 0.1 and 0.5, because when we say x is 0, it means I don't care what y is. Okay, so the rule is that in order to compute the marginal distribution of x, we sum over all values of the other variables. In this case, it's just y, because we don't care what they are. And so the total probability of x being 0 is just the sum 0.6. And of course, the other one is the complement, so it's 0.4. And that's called the marginal distribution of x. Okay, so hopefully that clarifies exactly what a marginal is. Okay, so we just keep x to be 0, and we sum over all other values of all the other variables, because, and this is again nothing more than the law of total probability. The law of total probability says that, for a particular event, we just take the conditional and sum it up. In this case, we're not using conditionals, we're just doing it sort of, it's clear, it's so simple, we can just show it this way. In the same way, the marginal of y is going to be Py, y equals 0, Py, y equals, a, y equals b. Well, y is equal a, and then we sum over this, so it's 0.1 plus 2, it's 0.3, and this is going to be 0.7. Okay, and we see that this is how we find the marginal distribution of y. Okay, so we can think of the marginal as saying, I'm giving you the joint distribution, and now just ignore that x ever happened. You know, just forget the process x. Just tell me what's the probability distribution of y. That's the marginal distribution. Okay, and the reason we call it the marginal is because this is the margin right here. Right? This is the margin of the sheet of paper, so to speak, with the joint distribution. So I just sum across the rows this way to get the marginal distribution of x. This way I get the distribution of y. That's exactly what I'm doing over there. Okay. So next question is, are a and b, x and y independent? Well, if x and y are independent, then probability, for example, 0a is going to be probability x, 0 times probability y, a, for example. So probability 0a is 0.1, and is that equal to, no, it's not equal to, px0 is 0.6 times 0.3, because this is 0.18. So it's not the same, so they're not independent. If they were independent, this would work out, right? So it's not independent. And of course, the other probabilities aren't going to work out either. Okay? Any questions about that? Yeah?
The problem in the exam should be independent, because we don't have time to check all of this.
Even if one of them doesn't work, it's good enough. It's not independent.
So the solution is clear, because we know that the problem with the exam is not because we don't expect us to check all of the situations in the exam.
Yeah, that's called a meta answer. Okay, and the answer would be, had it been independent, you would not have asked the question, and therefore it's not independent, and I would give you a 0 for that. Okay. Okay, you can be too clever sometimes. Okay, you meaning one can be too clever sometimes. Okay, so the next concept I want to get across is the notion of a conditional probability distribution, and I'm going to explain it, and then I'll do the homework. And really, Bayesian network, which I guess I'm not going to cover, is nothing more than conditional probability distributions. And so I'll say a couple of words about it, but let me talk about conditional distribution first. So we have the following situation where I have some random variable, let's say x, another random variable y. And what's going on is that y has some domain. Actually, let me first do the thing. I'm going to first generalize it before I go to the conditional. Okay, so the 3 generalizations we can do over here first. Well, the first obvious generalization is that instead of having a domain 0, 1, I could have essentially a domain which had lots of values. Okay, that's a straightforward generalization. There's no particular reason it should have only 1. Only 2 it could have, n. So that's a straightforward generalization. In this case, if you have m over here, n, then the joint is going to have mn, as we already talked about before. The second generalization is that we could have x and y be continuous random variables. If x is continuous and y is continuous, then what is the xy distribution? We can implicitly define it by the following equation, pxy of the value xy, okay, which we write as, this means actually pxy. Okay, I'll just write the equation here. Yeah, let me do this properly. P xy, a is less than equal to x, less than equal to a plus alpha, and I'll just write and instead of the b is less than equal to y, less than equal to b plus beta is equal to this integral, so double integral, b to b plus beta, integral a to a plus alpha, p xy, xy, dx, dy. Okay. So, all right. So it's not a p. It's just, yeah. So what we're saying is that let's say we have two variables, two variables x and y that are continuous random variables. I want to tell you what is the density function of the continuous random variable, joint random variable xy. So xy is the joint variable. What is its density function? Remember, we can't do probabilities and products anymore because it's the density function is not probabilities, right? It's just the density. So I need to define the density, and if you remember, the way we define density functions was that the amount of probability mass in the range between x and x plus delta, or minus delta by 2 is less than x plus delta by 2. So in that little strip is given by the integral of the density function fx, right? In our case, what we're saying over here is that the density function pxy is given by the fact that the amount of probability mass that lies in the small range between a and a plus alpha and b plus beta is given by the integral, or the double integral, which is going to be some area corresponding to this small neighborhood between a and b and a plus alpha, a plus beta. Okay, and that's basically how we are viewing it. So in some sense, the product of these random variables defines a space in which the probability mass kind of so in a two-dimensional case, we had sort of fx or something like this, and we had this x to x plus alpha, and we took this mass over here. In this case, we can think of a surface, and there's some surface like this, and we choose this is x, this is y, and this is the probability xy of xy. And so we take some small region, okay, and we're looking at sort of the volume over here. And this is in some region xy, so we have, it's like a smallish thing, and we have AB, and then we have the parameters AB, A plus alpha, B plus beta. And so that double integral tells us the amount of probability, okay, that is in that region as being this double integral over here. So this is the sort of the definition of the continuous random variables. Now again, in almost all cases in computer networking, we never use this. We typically end up with discrete random variables. We rarely use continuous, but anyway, this is more for completeness, and it's a sort of a generalization of the density function, continuous density function, rather than using discrete distributions over here. Okay, any questions? So it's just a okay. All right. So now let me go back to this issue of conditional distributions. Before, okay. So the conditional distribution, what happens is this. Okay. I have some random variable x and have some random variable y, okay, and x has some domain, and then y has some domain which I don't have to state, okay. Now here's what's going on. We have some distribution of y, okay, which is, let's call it, which is something, but if I know that x has taken on a particular value, okay, so x has taken on this value over here, then in fact y's distribution changes, okay. So knowing that x has taken on a particular value changes the distribution of y, and if it takes on a different value, it changes another distribution of y, okay. So to take a practical example, we had this rain and cloud example. So let's say we have a random variable which defines, we can say that tomorrow we're going to have 0 and 10% chance of rain, 10 to 20% chance of rain, and so on. So we have, let's say, 10 discrete bins, and so the domain of the random variable is going to be 10 different values, okay. So if I were to draw it, I'd say 0 to 10% chance of rain tomorrow, 11 to 20%, etc. So I have some set of bins like this, and if I have y, which is a random variable which takes one of these discrete values, I can certainly assign probabilities to each of these values over here like so, and this corresponds to, or this is the distribution of y, okay. So this is the distribution of the discrete random variable, which is the probability of rain tomorrow according to these bins, right. That's a perfectly reasonable random variable to have. Now I tell you that, by the way, it's cloudy today, okay. And if it's cloudy today, I can assume that these values change, okay. And if it's not cloudy today, it has different sets of values, okay. So the distribution of y itself is conditional, on the values taken by x. And that is what we mean by conditional distribution. It's not a conditional event anymore, but it's a conditional distribution. And there's a distinction between the two. A conditional event says this event happens depending upon what I tell you, right? Like, however, here the distribution is changing as depending on x, and this is what you define as p x given y. So and the definition actually is pretty straightforward. We say that p y given x is going to be x y y given x. Y given x is going to be equal to p x y, the joint distribution x y over p y y. Okay, so that's the definition of p y given x. Similarly, p x given y, because you can do it the other way, is going to be the p x y divided by p x x. So to show this, let's look at this one here and look at the what is p x y. So what is p x given y 1 given a, okay, over here. Okay. So to compute this, what we're going to do is this is going to be the joint probability pxy of the event, joint event 1a divided by py of the probability a. And this one, probability of 1a is 0.2, we know that. And py of a is just 0.3, and this is going to be 0.6. And then p y given x of a given 1 is going to be p x y of 1a over p x of 1. This is going to be 0.2 again, divided by, what's the probability x is 1? Well, that is going to be 0.4. So it goes to 0.5. Okay, and so those are the answers for the homework problem. So the main concept I want to get across here is that the distribution of y changes knowing what x is. So here I'm basically telling you what is the probability that y takes on a particular value here, given that x is over here. And this is going to change when we do the, yeah. Point 2 by 3. Well, it's 0.666, whatever. I was going to put the bar on top. Okay. This one. Yeah. Say that again. Above it. Yeah. Pxy, xy over pyy.
It's y given x. It's y given x, so it will be divided by
x. What am I doing here? Oops, sorry. Px, so I messed this up. Okay, px, x. Right, it will be x. So this is going to be, this one is correct? Yeah. Oh, that's right, x given y. Yeah, sorry, that's fine. Yeah, I just made a typo there. Yeah. It's not even a typo, it's whatever. Okay, thank you. So we'll start with information theory on Monday. Okay. We'll get more into this at that time.